Okay, so first of all, good afternoon, everybody. It's a great pleasure to introduce Rangel Baldasso from University of Leiden, and he's gonna talk about sharp thresholds for Glauber dynamics percolation. Rangel, the room is
Yes.
yours.
So thank you very much, Marcelo, for the invitation, and thank you everybody for joining in today. So as Marcelo said, I'm going to talk about sharp thresholds for Glauber dynamics percolation. And please stop me at any time if you have any questions, and don't be shy. Okay, so this is a joint work with Caio Alves, Gideon Amir, and August Teixeira. And we are actually finishing it up like in the following weeks. So it should be on archive quite soon, I would say. And the goal of the project is to start to understand percolation models that come from looking at the state of a particle system in some finite time. So here you can think of something like, let's say, we take the Volter model, or take, for example, the contact process. Any particle system that you'd like, and you can look at the configuration at some fixed time, eta t, for example, let's say, as a percolation model on Z2 that has some spatial dependencies. And for this talk here, I'm going to focus on Glauber dynamics for beta equals 0. So in the infinite temperature case, because it's a simpler case for us to analyze here. So let me quickly start to define this process. First, we will start with an IID initial condition with some given density rho here. So with probability rho, a given site it starts with opinion 1 with probability rho and opinion minus 1 with probability 1 minus rho. And each site will then update with rate 1, and it will match the majority of the neighbors. So for example, if you have an update here, let's say this site here has an update, and you have +1, +1, +1, and -1, this new guy here in the middle will update to become a +1. Maybe it was a +1 beforehand, so it won't change anything. And yeah, so that's the update rule, and it happens with rate 1. And the second thing we have to establish is how ties are solved, because it might be the case that you have a site here that has 2 +1 neighbors and 2 -1 neighbors. And in this case here, if you have a tie, we're gonna only resample this new site here to be +or -1 with probability 1/2 independently of everything else. So yeah, that's it for the model. There's like I'm gonna talk a little bit about the graphical construction of the model because it's gonna be useful for us later. There's a question in the
Rangel, there's a question by...
Things change if you take say the hexagonal lattice. So no, you can do the same things for the hexagonal lattice. You need to do, for our things to work, you can, anything that has like some nice duality properties should be fine. So triangular lattice, hexagonal lattice. But what I'm going to talk here today, if you're talking about like the hexagonal lattice, so in the hexagonal lattice, the critical point for percolation is 1/2. And what I'm going to tell you today will imply that this critical percolation is constant over time. So if you run your dynamics to any finite time, the critical percolation is still equal to 1/2. Okay, so let's see a quick graphical construction here, which is very simple. You just take each site in Z2 receives a Poisson point process. Let's call it this Poisson point process Px that has rate 1, and also a sequence of ±1 random variables, which are used, these random variables here, which are used to update the opinions in case of a tie. Now, so the way it happens, you fix a site here, for example. If you want to see you run the process here from time 0 to time t here on top, for example. We run the opinion of the guy here, and whenever we get to a clock tick, we update according to the local rule that you have. If you have a tie, this guy will receive a -1, and then you just continue going upwards in time until you can determine the opinion of this guy here at time, and then any time t that you want. Okay. So, as I said, our goal here then is to fix some finite time t. So this time t is finite, and to examine the percolation model that you obtain. Here's the site percolation model that you obtain by looking at the configuration of your particle system at time t. And this is a percolation model that depends. So maybe here depends on the initial density rho. So we want to see what can we say about the percolation at time t, about percolation at time t as a function of the initial density rho. And our theorem here is for any fixed time, there exists some critical percolation, some critical density that depends on t, such that if you are above t, above rho c of t, then you are supercritical. If you are below it, you are subcritical. And if you are exactly at rho c of t, then this guy here is a critical percolation model. And furthermore, we also have some root estimates. So the probability of crossing an n by n box at distance n, crossing an n by n box at time t is bounded from above and below by some positive constant. Maybe here it's something that we should mention here is, for example, that this rho c of t here is not clear that it is not equal to 0 or 1. So one of the questions that you need to ask is this guy here different than 0 and 1? This is true in the case of zero temperature Glauber dynamics. But it's not true in general, so it's something that we need to check. So our more general result says when let me see. So when you have a non-critical phase transition, then this behavior always happens. Maybe I think here on top I said beta equals 0, so I think that was incorrect. Okay, well, it doesn't matter, it's 0 temperature, so.
I think it's a bit above, yeah, it's
I lost it.
0 there, so yeah, right there.
Yeah, so here is 0 temperature. So that you have, and this is beta equals infinity. Okay. I'm sorry.
Rangel, I have a question. Do you know how the critical parameter depends on time?
Yeah, so that's something you cannot answer yet. We know that for the hexagonal lattice, the critical parameter is always equal to 1/2. But on the
for any time.
Z2, for any time, yes.
And why this happen?
Well, this happens because of symmetry. So you know that this is true at time 0, and it cannot. Okay, let me see if I have an easy way to answer it. So you have this kind of the hexagonal is very special because you have this symmetry, and then you cannot if you increase or decrease the critical threshold, then you would have a whole interval where you don't have percolation neither of -1 sides nor +1 sites, and that cannot happen, precisely because of our sharp threshold result here. So I can go in more details later, maybe. And but it's because of self-duality, self-duality. Okay. So maybe here like two small remarks about the theorem here. First of all, is that this is like an annealed sharp threshold result with respect to the initial condition. So in the case that, in the sense that you don't really need to condition on the realization of the clocks, and it's actually not clearly true that something like this should happen when you condition on the realization of the clocks. And yes, and also similar statements also hold for other particle systems, but you need some conditions on the particle system being considered. So something like attractiveness, it's something that you need, but also like also we need to know that a configuration at time t, let's say eta t, satisfies FKG, for example. Satisfies, which is not entirely it's not immediate, but it's true for several natural models like the Volta model or the contact process.
Rangel?
Yes.
One question. This is also true for, do you know any example with continuous state? I mean, instead of plus and minus 1, if the spin state values on the circle or on the 0-1 interval?
I suppose you could do something like that and then look for like something of the sort, percolation of the level sets, so something of this sort. And I think here, and I think it should kind of work too in this case.
Okay.
But I'm not completely sure that everything should work out fine. Okay. So maybe, so now I would like to go back to independent percolation to show you what is the usual not usual, but the recent technique that has been used to prove theorems of this sort. And we're going to consider here site percolation. So consider sites of the two that are open independently with some probability P, and that's P in 0, 1, but you can also do the same thing for edges. In our case, since our first model here is a site percolation model, we're gonna study site percolation. And the first thing to observe is that we can relate the existence of percolation, that's the existence of an infinite connected component, with the box crossing probabilities. So what is the box crossing probabilities? It has to do with this box crossing event here on the right that says that if you have a rectangle that's of size lambda n by n, you have a left to right crossing here by open sites. And the first proposition that you prove is what's called a finite size criterion. So it relates probabilities of these crossing events here to the existence of percolation. So to a value of P being on the supercritical or on the subcritical phase. So the finite size criterion says the following. It says that there exists some positive constant C such that if you have a P such that the probability of crossing a 3n by n box is large enough, meaning larger than 1 minus C, for some value of n. So if there exists some n such that this probability is large enough, then you have percolation. So you are in the supercritical phase. And on the other hand, if this probability of crossing is small enough, then no percolation occurs and you are in the subcritical phase. Okay, so once you have something like this finite size criterion, you can divide the interval 0, 1 into 3 different intervals by defining what is called the fictitious regime. So we're going to define P plus as the least value of P, such that the condition of the first statement here in the theorem holds. So P plus is the infimum of all the P's such that this condition holds. Analogously, P minus is the maximum P such that the second condition holds. And this splits our interval into 3 possible cases. So first of all, we have the interval from 0 to P minus, which is subcritical by the first result. Second, we have the interval from P plus to P to 1, this interval here, which is supercritical by our result again. And in the third window here, we have this critical interval, which is called the fictitious regime. And in all of this critical interval, very weird things happen. And the goal is to study this critical interval and actually show that it can be, that it must be always 1 point. So the goal is to show that P minus is equal to P plus. And okay, so from now on, what we want to do is to study this critical regime, this critical interval. And the property that we know from this critical interval is that probability of crossings 3n by n boxes are bounded away from 0 and 1. So in this critical interval here, we have that P, this probability here, 3n by n, is at most 1 minus c and is at least c. So this is the property, this is the central property. And this actually has several implications. The first of all is the Resumo estimate that says that this is not only true for rectangles of size 3n by n, but also for any aspect ratio that you want. So if you look at lambda n by n, then the probability of crossing boxes of this aspect ratio is also bounded away from 0 and 1. And the second tool that we need here is what's called a one-arm estimate. So it's related to the probability of having a box of side length n. So here's 2n, but it's kind of the same. And asking what is the probability that the center of the box is connected to its boundary. And what you can prove if you're in this critical regime is that these probabilities have a polynomial decay. So there exists some gamma such that the probability of connecting to distance n from the origin is at most n to the minus gamma for all n that you can choose.
Rangel, may I ask maybe a very stupid question? Mm-hmm. Is it clear from the definition that P minus is smaller or equal to P plus?
Yes, because you know that below P minus you have supercritical, so no infinite components. Mm-hmm. So if it were like this, let's look here. You have P plus here and P minus here. So here in the middle, from the first statement, we would have an infinite component, but from the second statement, no infinite component would appear. So that cannot happen.
Yeah.
So this is cannot happen. Thank you. Okay, so these are the only two two tools that we need in order to prove our theorem that says P minus is equal to P plus, and actually it's equal to PC, so the critical probability percolation. Critical percolation probability. Okay, so in order to prove this theorem, I'm gonna do a quick sketch here because it's gonna be useful for us later. We rely on something that's called a randomized algorithm. So what is a randomized algorithm? We start with a Boolean function. So we have a function f that's Boolean, so from -1, 1, 2. Maybe here it's better to put -1, 1, 2 to keep the same notation, but it's kind of doesn't matter. And now we're going to have an algorithm to determine this function. So what is an algorithm to determine this function is the following. You have an entry of this function and you want to say what's the outcome. So you have f, you have some omega, and we apply our algorithm and you want to get as an outcome of this algorithm f of omega. And an algorithm is just a rule for observing bits of your entry one at a time. And you stop at when you know what is the value of f of omega. So, for example, let's say that your f of omega is actually the value of the first coordinate. An algorithm would be observe the first coordinate. So it's kind of clear, but or another algorithm which is very useless here is observe all the bits, and then of course you have all information about your entry, and then you can determine the function. So yeah, so just to summarize, it's a rule that gives you an order in which you reveal bits, and in the end you need to be able to determine what is the value of f. And so this is a function, it is an algorithm that determines the function f. And given the algorithm, you can define what's the revealment of this algorithm. So for some x in n.
Rangel,
Yes.
can you repeat what's the difference between the function and the algorithm?
Yes, so you have the function. The function is something that takes -1, 1 to the n to 0, 1 to -1, 1, right?
And you want to determine the function.
No, you already know what is the function. Like the function is, let's say, the majority of the guys here. It tells if the majority is plus or -1. Okay?
Okay.
And then you have an entry here, omega 1, omega 2, until omega 5, let's say, and you want to say what is the outcome. Okay?
Okay.
But you don't know what are the entries. You don't know if they are plus or -1. So your algorithm will look at them and say, okay, so the first one that I want to look is omega 4. And then you come here and your algorithm looks for omega 4 and says, oh, omega 4 is 1. And then it says, okay, now I looked omega 4 and it's 1. So now the second one I want to look is omega 3. And then you come to omega 3 and then it looks and it's -1.
So an algorithm is a strategy to know the value of the function.
Yes, so it's a strategy. It's a Markovian strategy. So wherever you know, wherever you already observed, you can use as information to choose the next guy that you're going to observe.
Okay.
Yes, and then you stop as soon as you can determine your function.
I see.
So you say, let's say, if f is the majority of the plus or -1s here, and you observe these first guys here, you know that your fifth guy here cannot influence the value anymore because it cannot change the majority. It's always going to be +1 in this case.
So
right?
an algorithm is designed through the function, right?
Yeah,
you fix the function and design the algorithm.
Yeah, you fix the function and you design the algorithm.
Thanks.
Yes. Okay, so given the algorithm, you can define what's the revealment of the algorithm. And the revealment is the probability, the revealment is associated to an entry x, and it says what is the probability that you need to observe x while running your algorithm. Okay, so here, for example, if you start in our function, in our example here, that's the majority. If our algorithm always starts from 1 and goes until you know that you reach the majority, for example, the revealment of this bit is going to be 1, the revealment of this bit is going to be 1 as well, that the probability to observe it. And whenever you pass the halfway point here, that would be like omega 3, for example, then omega 4 would have a revealment smaller than 1, because it might be that the first half already determined that the function might be plus or -1. Okay. So yeah, so you have these algorithms that are the probability that your this revealment, that's the probability of the algorithm observing given entries. And you can relate this revealment with the variance of your function. So this is called the Oss inequality. And it says that the variance of your Boolean function is bounded from above by this weighted sum of influences. So have the influences here, that's the probability of your entry x being pivotal, meaning that whenever you change x, you change the outcome of the function. Whenever you change the entry of x, the outcome of the function is changed. And the variance is bounded by this weighted sum here. So maybe a note here is that since the revealment is a probability, it is bounded by 1. And this recovers here the Poincare inequality that says exactly this. So this is Poincare inequality. And it's a particular case of our OSS, of the OSS inequality. Okay. So in our case, the algorithm that you want is an algorithm that helps us determine the existence of crossings of a square. So our Boolean function here is whether or not you have a crossing of a 3n by n square. Here I drew a square, but and we want an algorithm that helps us determine whether or not you have a crossing. So the way this algorithm works is actually quite straightforward. First, you choose uniformly a starting point for a line here choose uniformly a vertical line between all the 3n possible entries. Given this line that you chose here, we start to explore all the sites that are on this line, and then you look at which sites are open and which sites are not. And from there, we explore the connected components of these sites. So whenever a site is open, you explore all their neighbors, and you continue this process by exploring neighbors of open sites that you already explored until you find all the connected components that are that touch this random vertical line inside the box. And in particular, if you have a crossing here, let's see, if you have a crossing, then you're gonna explore it for sure, because you're gonna have at some point all these guys here that are open are gonna be explored, and you can determine its existence via this algorithm. And of course, clearly, if you don't have a crossing, you're gonna know the whole connected component, and you won't be able to reach either the left or the right sides of the rectangle. Now, so what you need to do now is estimate the revealment of this theorem. Can you use extra randomness to define your algorithm? Yes, you can use extra randomness as long as it is independent of your entry. So for example, here, the extra randomness is choose a uniform vertical random line, which does not depend on your configuration. Yeah. Well, God, sorry. Okay, so
there is yet another question by Shun.
Yes, can you explain a bit about delta x of A? Okay, yes. So let me go back here. So you have this algorithm, right? It's like a random algorithm. So basically, it's a Markovian way of querying bits. So we start with like this bit. Maybe if you go to this example here, it's gonna be clear. We start with like some bit here, and then from that bit, we start to explore our connected component. From that entry here, we start to explore our connected component. And then we say, what is the probability that this guy here is revealed by our by our exploration process, by our algorithm that determines the existence of left to right crossings. This is delta x of A, is this probability. And you can see, for example, in this case here, that this guy here, it's only going to be revealed if the following happens. You need to have an open line that I'm going to draw it as red, even though that's not very good color for open. You need to have an open connected path from this guy here to the random vertical line that you chose. Okay. So if this guy is very far away from your line, then what you recover here is a one-arm. It's a one-arm event. So you see that you have like a box here of sides something, and you have a connection from it to the from its center to its boundary, which you know decays polynomially. Okay, so this is not a complete proof that you have this estimate here, because you still have the case when your vertex is actually very close to your line. But this is taken care by noticing that since you chose the vertical line at random, this probability is very small for a given guy. Okay, so now once you have this thing here, this bound here on the revealment, we can bound the variance via this sum here. So this variance here is bounded by this sum here of the influences, right? And the sum of influence, this is Druce's formula. The sum of the influences is actually the derivative of the probability of having a crossing. And okay, and the next ingredient we need, the last ingredient you need here is this bound on the variance, which is basically due to the fact that you know that the probability of this function being the probability of f being equal to 1 is at most C3 and at most 1 minus C3. So if you combine this inequality with the expression for the variance, you get this constant lower bound. And basically what this tells you is that in the critical interval, the derivative of this function here grows polynomially, right? Because you have that the derivative here is at most C3 squared and to the gamma prime. So it grows polynomially, and since this function needs to be between 0 and 1 because it's a probability, this critical interval cannot be very big. Actually, it's of polynomial size in n, and okay, that's written here. So this interval has size at most some constant n to the minus gamma prime for all n. So just take n to infinity, and you get that p plus is equal to p minus. Okay. There is FKG going on in the one-arm estimate. Yes. So there is to conclude the one-arm estimate here from the Russell-Walsh estimate. You need FKG and correlation decay, which here it's independent. So it's independent. It's in the independent case, so you don't need it. But it's basically a combination of one-arm of Russell-Walsh with FKG inequality. Okay, so now let's go back to our model here. So from now on, I'm gonna just consider a time t that's fixed, and I'm not gonna worry about it. So whenever I write some probabilities with respect to the process at time t, so 8 at t, and the strategy is to follow the same proof for the independent case, but there are some problems here that we're gonna see soon enough. So first you need to prove the finite size criteria, which is exactly the same, and this relies on renormalization. Plus correlation decay. So it's written here again. Okay, so this relies on renormalization plus estimates on the correlation decay for our model at time t. And these correlation decays for the model at time t, they actually come from something that's called the cone of flight estimates. So this is basically the biggest set we need to observe in order to determine an opinion of some guy at time t. So we go back to the graphical construction that I introduced in the beginning. Each vertex has a Poisson point process with intensity 1. And in order to determine the opinion of this guy here at time t, what you need to do is you go back in time until the first clock ring and expand this set here to contain all the neighbors, and keep going back on time, always expanding when you reach the clock ring until the point you reach time 0. And then from our graphical construction, we know that for sure these guys here that go from the cone of flight of this guy here are exactly exactly what you need in order to determine the opinion at time t. And it turns out that the size of this cone of flight here decays very quickly. So the probability that this cone of flight reaches the distance bigger than n decays as e to the minus c n to the n log n. So it's even faster than an exponential. And this tells us that our percolation model has faster than exponential correlation decay, which is actually very important. Our techniques don't work if you only have exponential decay, which is quite surprising. And yes, so once you have this cone of flight estimates, you get the finite size criteria. And analogously to the previous case, you can define the two critical densities, so the rho plus and the rho minus, as the minimum and maximum values for which our result applies. And then what's left is to study the interval, the interval densities between rho minus and rho plus. And if you continue with our approach here, first we need some Russell-Welch estimates, which are provided by a recent paper by 2020, I think, by Kohler, Schindler, and Vasantasian. And they basically said that under very general assumptions on your percolation model, you have RSW estimates. And again, here combining correlation decay plus Russell-Welch and FKG, we get the same one-arm estimate that we have in the independent case. Okay. So now it would be very nice if you could apply the same ideas from the dependent case, but the problem is that in order to do that, we cannot work with the randomness that comes from the clock peak that you have in your graphical construction. So one possible way to do that would be to fix the graphical construction that you have. So work in the quenched case. So fix the collection piece. So fix Px, let's say. These are the clocks in the graphical construction, and then work on the quenched case. So all the clocks are fixed, and then you only have the randomness of the initial condition. The problem with that is that here you lose these two good properties here, because these are annealed properties. So these actually rely on the existence, on the randomness of the graphical construction. So yeah, so that's the problem. You lose these two properties, and a way to solve that is to use an alternative graphical construction. So the second graphical construction is going to be quite similar, but you're going to have more randomness to work with. So in this graphical construction, we fix some positive integer k, and each site now will receive a Poisson point process of intensity k instead of intensity 1, which means that you have k times more clock ticks. And now clock ticks are ignored with probability 1 over k. So we have this denser collection of clocks, but whenever you reach a clock tick, you can decide whether or not you use it to evolve a process, or if it's just there, like it's an invisible clock tick for you. Let's put it. And now, why is this graphical construction useful? Because you can have some concentration estimates for annealed quantities. So if you have any function here that depends on your configuration at time t, and you condition it on the collection of clocks of intensity k, so here's intensity k, this function here has a small variance, this conditional expectation here, meaning that it's very likely that you retain some information from your annealed configuration when you condition these things with larger density. So, and basically it's very useful to solve the problem. You can use the same strategy as in this quenched configuration, but quenched on this larger density in this configuration in this construction with an increased density. And then what to do is copy the proof the same way a bit. Let's see. So you can use the same algorithm, but now since you're only fixing the denser collection of clock ticks, your algorithm also needs to observe whether time ticks are selected or not. So you have two different types of entries that your algorithm observes: initial conditions and clock tick selections, which appears here in this OSS as inequality here that you're applying. So here, if you see the OSS here, we get the variance of our function conditioned on the denser collection of clocks is at most the revealment of the algorithm for the initial condition. Here in this guy here is the initial condition plus the revealment of the clock ticks. Because whenever you have a clock tick, you still need to see whether you want it to be selected or not. And that's a whole new set of entries that your Boolean function needs to take into account. And yes, so, and the second thing that you have here is a bound on the revealment. So now it's an annealed bound. You need to say that conditioned on the configuration, these revealments are very unlikely to be large, which is exactly what this says. This probability here is then on the denser sets of clocks. Yes, there we go. And the third ingredient, it's a kind of Russo's formula, which is again a conditional Russo's formula, but we only have the sum of the influence of the initial condition here. So somehow we need to relate this other sum here on top to this first sum that appears here. And this is the equivalent of relating the influence of a clock tick to the influence of initial conditions. That's maybe the hardest part of this whole thing here. So maybe let me tell you a little bit about what's the idea of how to make this kind of like Eisenman agreement relation here. So let's say, for example, we have a clock tick here in the middle of the box XS that's pivotal, meaning that whether we accept it or not changes the existence of a crossing at time t here in our configuration. So if you look at the cone of flight to the future here of this guy here, we have some shape here on top. And this shape here, you know that you have crossings from left to right and from top to bottom. that are open and closed. So these are open, these are closed. And you also know that the radius of this thing, due to our correlation decay estimate, is actually of order smaller than log n. So it's log n over log n, let's say. Okay, so now what you want to do is to make a local modification of our selections of clocks and initial conditions in order to obtain some vertex here in the time at time 0 that's pivotal. Okay, maybe if you are considering, for example, the Volter model, what would happen here is that this guy here is for sure the copy of some guy at time 0. And since it's the copy of this guy at time 0, if this vertex here is pivotal, this guy at time 0 is also pivotal. So it's much easier to relate pivotalities of clock ticks to pivotalities of initial conditions when you're dealing with the Volter model, but this is not the case anymore for Glauber dynamics, precisely because the opinion of a guy is not of a vertex not formed by copying something, but looking at several values and combining them in some weird way, or taking the majority of them. So what you do is we define a transformation of our entries here that change pivotality of time 0 to pivotality of a set of a contour at time. Sorry, change pivotality at some time s to pivotality of a contour here at time 0. In the following way, we look at the cone of light of the past here and take a circuit that contains it. And in this circle here, we're gonna first of all take all the clock rings in the shell here that we have forming the circle and freeze them. So no clock will be selected there. And then either we put the initial opinions here all equal to -1 or all equal to 1. And then it's not very hard to see that if you put all the opinions to +1, then you have a crossing at time t. And if you put all the opinions to -1, then no crossing at time t appears. So what this does, it changes pivotality of a clock tick to pivotality of some random circuit, of some circuit here around the origin. And you can estimate the size of the circuit because we know that we know how large is the cone of light of a vertex. Now, okay, so now since we have pivotality of this whole guy here, we simply go and start with configuration all -1 and start and change one at a time until eventually some vertex is pivotal. Because we know that if we change all of them, there will be one that's going to be pivotal. So that's the easier part. Maybe just to finish up, what you get is something like this. The influence of a clock tick is this term here that comes from forbidding. Is this how right? Forbidding clock ticks. Clock ticks on C. And once you forbid clock ticks on C, and as I said, the circuit C is jointly pivotal. And then if we change one guy at a time, we get this other contribution here that's of the exponential. It's exponential on the size of C times the sum of influences. And now what we use is that the size of the circuit is actually smaller than exponential. So it's of order smaller than, sorry, the size of the circuit is of order smaller than logarithm. So get that this thing here actually contribute to something that's small O of n to the epsilon for any epsilon that you want. So the price you need to pay to change pivotalities is is smaller than any polynomial price that you might want. In particular, it is small enough for you to for it to not matter when combined with this polynomial estimate that you have on the revealment. So you know that with very large probability, the revealment is at most n to the minus gamma, and the price you need to pay is not large enough as to cancel this n to the minus gamma that you have here. And yeah, so I think that's all I wanted to tell you, and thank you. And yeah, so any questions or comments?
Okay, first of all, let us thank Rangel. All right, are there questions? Shanji has a question. Why?
No, it depends on T, but here is everything's for fixed T. So actually, if you could get a bound that doesn't depend on T, you could prove like results have to be stronger because it would be uniform on the value of T. So what is true is that the constants, the bounds, they get worse as you increase T. But if you fix some value of T, you have a uniform bound that's worth for all the interval 0 T. Yeah.
Rangel, in your randomized algorithm, how do you choose the random line at first place? The random.
You choose it uniformly at random between all the lines, all vertical lines, yeah.
And I think I missed, why is it important that this line is like random instead of being just the center line?
Yeah, so that's important. Let's go back. So that's important here because I said that if your guy is far away from if the guy that you're observing is far away from the line, you can prove that it has low revealment via one-arm estimates. But if it's close to the line, then it would have a very large revealment. If you take, for example, a deterministic line.
Okay.
But since you're not taking a deterministic line, you can say it's very unlikely that a given vertex is next to the line because you have lots of room for the line. Yeah.
All right.
Can I make a question?
Yeah.
So you gave an example of the hexagonal lattice in which the density in function of t is constant. So you have no control over how this density varies over time, right? So do you have any example that it changes, for instance?
So no, for example, if you take if you take the case of let's go down here. If you take, for example, Z2 and you break ties, keeping your opinion, then what happens is that the critical point at some value t, it's always smaller than the critical time at time 0, the critical probability at time 0. So you strictly decrease the probability as long as as soon as you start running your dynamics.
I see.
Yeah. So that's an example where it's not constant.
Okay, nice.
Are there more questions? Okay, if not, then I propose that we clap for Rangel again. Okay, so thank you very much, and Rangel for the talk.
Thank you.
And, yeah, thank you everybody. I think that next week we continue with Tom Alford, if I'm not mistaken. All right, see you guys.